can start.
Okay. All right. So right now, let's talk about it's not really a new thing because I think you're already familiar with the supervised learning. It's just that you really have to consider your dependent variables or your target classes. So again, if we are to convert our unsupervised learning to supervised learning, you have to check this your main raw data, the one with ID and the one with IV. But you have to create another computation for your two target variables. Since you have two target variables, we wanted to find the average of these, all of your ID. So you can just see your average, calculate the average, then drag down. And then next is to round off to 0 decimal point, and then drag down again. So now that you already know your rounded off average value, you also wanted to check the frequency of all our values. So from 1 to 5, we have to put count if this one, range of your round off values up until this one. And then this is your criteria. So let's make it constant. Okay. So let's check if it's equivalent to 509. It should be equivalent to 509. Okay, there you go. So why do we need to also check the frequency? Because we wanted to ensure that everything has at least one value. So it's already fine if you have just one value just for the number one in the 5-point Likert scale. Because if you don't have any value for this part, you'll definitely have an error in your main algorithm, maybe for your PSOK means or for your ENN. So what are you going to do if you don't have, let's say this is equivalent to 0? You have to eliminate that participant number. So for example, this is let's just say we rounded it off that all of their values are 0. So this one, mm, okay, so for example, this one you already know that these is already averaged to 0. You have to eliminate everything. You just have to eliminate your participants. So from 509, now you already have your 508 participants. Okay, so please don't forget that one. Okay. And next, you also have to do the same part for your IV, or intention to visit. You can follow the same method, find their average, and then round off. After rounding off, find their frequency numbers. Count if CP. I'll change this one to CO. Okay. CO, why? Because we wanted to find how many frequencies do we have for these IV average round off part. And then we'll find the total. Just to be sure, it should be 509. Okay, so all of them also have at least one value. So this already means that we already have our supervised learning. So you can just copy this part, just this part, the round off part. Let me, for example, let me copy this one up until FC6. I'll remove this. copy this one, ID average round off in this part, paste values. This will be your new ID or intention to donate. And then copy your intention to visit, average round of values, and then paste. So this is already your supervised learning. Mm-hmm. Okay, so you don't need, if you're going to utilize PSO and K-means algorithm, you don't need to find the average values of FC1, FC2, FC3, FC4, and so on. You just have to focus on your target variables, intention to donate and intention to visit. So what comes next once you have these sheet? So you can actually apply your structural equation modeling, the factor loading from the SEM part. So let's say in the factor loading and in the significant the connection that has significant a relationship. For example, if your FC is directly significant to ID, and then you already knew that FC2, for example, it fell behind the zero point 0.7 or zero point 0.5 factor loading, you can remove this part. So you can just already remove them in this part. Again, this procedure is for the PSOK means algorithm. So once you remove them, you don't need to do anything again, but you just have to replace your Excel file in this part. So you have to create your new Excel file again, but this time you actually don't need to focus in PSO and K-means algorithm. You don't need to focus on this part if you're going to apply your SEM factor loading and SEM connection, the significant connection between all your latent variables. You don't need this part, so you can just delete them. But if you're going to use another method, so let's say you can utilize other statistical techniques, such as, let's say, correlation. So for example, in correlation, I'll input this one, the ID and IV. I'll open my SPSS, and then let's open your data. Desktop. Mhm, this one. So why do we need to incorporate our, oh, I have variables. I'll just remove the variables. Mm, I'll try it again. Mm, mm, Okay, what are these? It's been so long since I used SPSS. Yes. No.
What's that? It's
I
so
don't
weird.
know as well.
Oh, I think they
I thought
use.
I'm
I think because of the CSV or something like the file. No.
oh, is it CSV?
I think yes because it's CSV.
Oh, okay, okay. I'll just change it. That's why it's a bit
That's why.
unfamiliar to me.
Yeah,
I'll
it's a
just
little bit.
save it.
Yeah,
Okay.
perhaps like yeah, because that's actually for the
Uh,
running the smart PLS. Yeah.
Okay, okay. Okay, this one. Mhm. Okay, yes, it should be like this. Okay, it should be in Excel
See?
SX file, not CSV.
Yes. Yes.
Okay, so if you're going to not focus on the SEM part, because you can just actually you can create two different papers, and instead of combining SEM and then machine learning, you can just utilize the most simple, the simplest, I would say, the simplest correlation or statistics formula. So you can just find the correlation, so correlate and then bivariate. So you can just put everything in this part to tail. Okay. And then you can find actually the significant one would be the ones with asterisk. I think the ones with two asterisk would be the most significant one at this one 0.00 and one asterisk for 0.05. But in this part, you need to focus on IV and ID. Where it? Okay, this one. So you just have to focus on the latent variables correlation with your ID and IV. So you can pick whether you want 0.05 or 0.01 significance value, and then remove the ones that are not significant to your ID or IV. So you can just remove them directly in these. mm, Oh, I removed this one. You can directly remove them in these Excel sheets. So for example, I noticed that these is not, let's look for one. Are they all significant?
I think so.
Okay, if they are all significant, you can utilize this part instead. The person correlation part, the value, actually we must have a very low value. Okay, so in some studies, they actually want at least zero point 0.5, but in other studies, they're very much lenient when it comes to the person correlation. So zero point 0.4 is also another acceptable value for person correlation. So if you really wanted to, let's say, focus on the most important variables, you can utilize or find some studies that focus on the zero point 0.4, if I remember it correctly. I think it's zero point 0.4, and then eliminate your Pearson correlation values below zero point 0.4. So for example, I'll pick this one because it has 0.321, although it's significant at 0.01. This is EE1. You just have to eliminate EE1 in this part. Okay, so eliminate everything that you don't deem not much significant to your model, and then run it again in this PSO k-means clustering. But again, you have to consider, let's say, two Excel files. Because, why two Excel files? Because, let's go back in this part. Because in this part, you can check your ID first or your intention to donate target class variable. So once you have eliminated everything from your target class variables ID, you can just create a new Excel file for your IV. Because for example, if you're going to utilize zero point 0.4 in ID, your EE3 is significant or is acceptable for the person correlation 0.41. But for IV, your EE3 is not acceptable because it's 0.365 below zero point 0.4. So you have to create different document for the two. And then,
Any questions?
mhm,
Omar, Jimmy, up to here. Okay.
okay. All right. So let's say you already have two different files. You also need to have two different models. So you have to run everything again. So instead of creating them in just one paper, I would suggest you can actually create two different papers. So let's say one for ID and one for IV. But in terms of having one concept, Turkey earthquake concept. You can also combine both of them, but think it might be too long as well, but you can also opt for the combination of the two or individual analysis of the two. Okay, so that's it up until this PSOK means how you can transform from from unsupervised learning to supervised learning. So apart from correlation, this is also another way for you. You can also utilize this one, analyze, and then where was it? This one, general linear model, and then univariate. So you can put your dependent variable here, ID, and then from EE1 to FC, this will be your fixed factors. And then click OK. Okay, so for your univariate analysis, okay, for univariate analysis, I often use this if I really wanted to eliminate a lot of variables because you can definitely eliminate a lot of variables without considering other factors. You just have to focus on your sigma. But one disadvantage of univariate selection is that it might have an overfitting once you input it into your PSO k-means algorithm. So you just really have to be wary of setting your right statistical analysis before you input them into your PSO k-means algorithm. And apart from these two, you can also explore a lot of statistical analysis before you transfer them to your PSO k-means algorithm. Okay. So yes, that's it for this part. So should we move Tokyogi to the ANN part?
Yes, let's go to
Okay.
ANN.
All right. So that's it for the PSO, K-means supervised learning. They actually have some similarities with our ANN. But before I talk about it, so let me share this one. Okay, so when we say ANN, we're talking about artificial neural network. Artificial neural network is a supervised learning. So we have to consider our ID and IV in this part. So if you notice, in ANN, we have these three primary layers. We have input layers, hidden layers, and output layers. Why do we need these three layers in ANN? Because ANN's primary purpose is to find it's actually almost similar to the SEM part. It's just that we have hidden layers. Because in ANN, we wanted to also find the most significant factors from our input layer. Okay, this is from our input layer with the help of hidden layers. When we say hidden layers, these are just the replicates of your input layer. So for example, I'll draw this one. For example, your input layer, this one is EE. I remember EE earlier. And then what else? UI, UI. And then let's say you have A, just an example. Let's say you have A. So all of your latent variables, except for your target class, should be your input layer. So if you have 8 latent variables except the target class, you have to input everything in this part, in the input layers. And you don't need to consider EE1, EE2, EE3, because later on we're going to find their average values. What is your hidden layer? Your hidden layer is just like your input layer. It's just a replicate of all your input layers. So if you have this one, you must also have this one. But the thing is, your hidden layer is completely random. You don't know whether you have A, maybe you have, let's say, mm, B in your input layer, but you don't have B in your hidden layer. So you can also have lower hidden layers. If you have, for example, if you have 5 input layers, you can have just 4 hidden layers. You can also have 6 input layers, but have 7 hidden layers. It's totally fine because it's also a matter of finding the perfect number when it comes to your model. So that's also the difference of ANN compared to the SEM, because in SEM, apart from not having this hidden layer, we can actually customize our own parameters as well.
Professor, sorry,
Mm-hmm.
can I ask a
Yes.
question?
Okay. Yes,
So,
please.
the input layer is the independent variables, right? Like
Yes. Yes. Yes,
so
that's correct.
so we will get the average for
Mm-hmm.
the right. So how is it possible that so if the hidden layer is just the replica of the input layer, how is it possible for the hidden layer to have more than the input layer?
Mm-hmm. Oh, yes. That's really a nice question because in ANN, let me show this part. In ANN, we have what we call as TensorFlow. I'll just type it because I have a poor handwriting. Mm, We have this one, what we call as TensorFlow and Matplot. So if we are to combine, what else? I think we also have NumPy and Pandas. So these are the common codes for ANN. When we combine TensorFlow and Matplot, we're actually combining the Python, the new program that we're going to utilize later on, the Python and this MATLAB file. So meaning we can actually explore other layers that are not evident in the input layers. So meaning it's like your, let's say, it's like your hidden card in order for you to match your accuracy. Because in ANN, you also have your bias neurons. And these bias neurons are also completely random. These are also random. And this helps you adjust to your hidden layer because in ANN, we don't necessarily assume that although we have found their average values, we don't necessarily assume that we have already considered everything, every factor into consideration. That's why the importance of both hidden layers and our bias neurons are all important because they kind of correlate each other. They kind of help each other to find the perfect accuracy of your model. So let's say what if you have increased your hidden layer, for example, from 7 to 6, but you might have multiple EE. You might even have multiple EE. So it might be too redundant. It might be too redundant, but then again, what if your EE is or has that overfitting value? If it has the overfitting value, it will not have a hidden layer of EE. It will automatically adjust. So instead of EE, it will find the best factor that neutralizes all your layers. So instead of EE, it might result in a lot of UI. Let's say a lot of UI that is based on your TensorFlow and your Matplot. Because in these codes, in these packages, you can find the neutralization of all your layers and of all your factors in terms of the overall model as well. So for NumPy and Pandas, I'll talk about it later on. But do you, or is it clear or a bit, a bit shaky?
A bit tricky, but I think I get the idea. Thank you.
Okay, all right. So just to summarize, I think I was not able to explain it as well. So just to summarize, mhm,
Basically, it's a black box, Omar. So we don't know what's inside, and
yes, that's the best explanation.
that's totally, and it's actually black box. Like sometimes, like you don't know why is it like that. Sometimes, but the most important for us is like we will get the accuracy later on.
Mhm.
Yeah.
Thank you for that, Tokyogi. So, literally, you actually you won't really know what are your hidden layers. Just as Tokyogi said, the model won't let us know what would be the best hidden layer. So you can definitely say that you have UI, a lot of UI here, but the thing is, it automatically adjusts to what kind of factor you wanted to have. Because, for example, you don't want too much overfitting on your model. You don't also want underfitting on your model. Overfitting meaning you don't want an accuracy of closer to 100 already. Because if you already have the closer to 100 in, let's say, in the first 10 runs, then that means you already have an overfitting accuracy value. Because as much as possible, you wanted to keep your model run so that it won't have any premature conversions. Okay. So let me clear this part. But for your output layer, these are your ID or your IV. Okay. So again, these are your latent variables. Latent variables for input layer and for your hidden layer, it's completely random. And for your output layer, these are your target variables or your dependent variables. And again, why do we have biased neurons? Biased neurons are always included in the input layer and hidden layer because it helps us neutralize everything. Mhm. But in actual model, we don't need to, by the way, we don't need to show the biased neurons. It's already normal whenever you have incorporated ANN into your model. It's already normal. But some studies might ask you to ask how many biased neurons you have. So if some reviewers would ask you, just include one because one is the standard for the ANN. Okay. So this is your ANN, but the difference to your deep neural network, this is DNN, what we call as deep neural network. If you notice, we only have one hidden layer in the ANN part. But for DNN, the only difference is that for ANN, we only have one hidden layer. But for the DNN, you can have multiple layers. Why do you need to have multiple layers? Because you wanted to increase your accuracy. So that's always the importance of hidden layers to always increase the accuracy of the model. Okay. Oh, and by the way, these are, I forgot, these circles are what we call as nodes. One thing to remember as well, these are your nodes, all the circles. Okay, and for the connection, everything is connected. If this one is connected to this one, if one is connected to two, this should also be connected to three. This should also be connected to four. So you have to remove the concept of your SEM part. You don't need to consider the relationships of one variable to another because in ANN, everything is connected. So everything must be connected. So in some studies as well, they want you to create this this figure, but I don't really suggest creating this figure not unless the reviewer would tell you to do so because this is already a standard. So in your study you can just mention that your input layers are these latent variables, your hidden layer not hidden layers. Let's say you have one hidden layer, two hidden layers, and then for your output layers, what are your target variables? Okay. So now let's move to the coding part. So for the coding part, you have to download this one. So we're going to utilize another coding tool. This is what we call as Python. So you can just freely download this one, Anaconda, then click download. And then it will lead you to this part. So once you already downloaded, this, don't worry, this is for free. You don't also need to sign in. But if it requires you to sign in, no payment at all. You have to install this one. Mhm. This one, PIP install TensorFlow. So once you have opened your Anaconda, you have to search this part, Anaconda, this PowerShell prompt, and then, oh no, sorry, not PowerShell prompt, this one, the one without PowerShell prompt. Run as administrator. Mhm. And then click yes. So we only need one. So you can just input PIP install TensorFlow. So a while ago, we already talked about the importance of TensorFlow because in TensorFlow, this is it's like your main package in order for you to run your ANN. So this will help you run all your hidden layers. It will help you neutralize everything. You can just click it. I've installed this already, but it may take time, so you can just wait for it just in case. Mhm. Okay, so you've already installed it once it creates this new line, this new system. So you can just erase this part. And then finally, out of all these tools, we can just focus on Python using Spider. Let's click launch. By the way, another tool that I wanted you to also explore, let's say you want a more user-friendly environment, I would recommend this part, Jupyter. I used this when I was still starting with my coding part, so I learned more in this one, Jupyter Notebook, compared to Spider. But you can actually transfer your Spider and Notebook codes for each other, so you can also utilize the same codes. But then again, Jupyter Notebook is more user-friendly for starters. So this is your Anaconda part, the Python part. Okay, so I'll create a new file. So if you create a new file, it will always leave into blank. And please don't forget to install your TensorFlow because if you fail to install it, you'll have your error later on. So I'll discuss the codes one by one. Okay, so for NumPy, when we say NumPy, we're talking about numerical Python. A while ago, if you noticed, we have lots of percentage in MATLAB. We use percentage in order to input some notes in this part, okay? Percentage. But in Python, we can use number sign instead of percentage sign. When we say numerical Python, we wanted to include all of the formulas, all of the operations. For example, if you wanted to add, you wanted to subtract, you wanted to divide your numbers, you have to include NumPy. Because if you won't include it, you can still add, you can still subtract, but not in array. What is array? In Python, when we say array, these are what we call as data in the brackets, like this. Because in Python, it automatically transforms your table values from this part to this part. And we wanted to, for example, we wanted to add them for 4, 5, 6, 7, 8. If you wanted to add them, it will become, for example, you're going to add your A and B, it will become 1 plus 4, 2 plus 5, 3 plus 6, 4 plus 7, 5 plus 8. So that's how the NumPy adds or operates your array. For pandas, when we say pandas, we wanted to consider our arrays. So this is always a combination. If you have NumPy, most of the time you also have your pandas because you won't be able to have these brackets if you don't have pandas. But what's the importance of pandas if you can just directly add everything as it is? Because in Python, it would be too difficult if you have missing records. So for example, like this one, I don't have any value in this part. You don't have any value, but you have to add this one. It will not result into 0. This is not 0. This is actually a null value. In the end, it will result into an error. So you always have to find the combination between NumPy and pandas. For matplot, again, for this import method, we wanted to find the similar codes from our MATLAB, this one, because actually MATLAB is also a combination of different programming languages. But in Spider, you don't get to apply some languages imported from this MATLAB. If you remember in our MATLAB, we just have to code everything as it is. We were not able to install something in order for us to run this entire model. But in Spider, we need to install a lot of packages because it's not incorporated into the Spider. So similar to this one, we also wanted to import Matplot's codes. I'll make it as untitled. So TensorFlow, a while ago we talked about the importance of TensorFlow. This is for your ANN package. And these two codes always come with each other because if you have import TensorFlow, you also have to import your keras. It also pertains to your ANN package. So this is like your solution package once you need to incorporate your ANN model. But what about your sklearn model or your train test split? It's important for us to find our training split and testing split. So in ANN, it's also about finding how many data are you going to put into your training split and testing split. Training split meaning you wanted to train your model first. For example, if you chose out of all your 100% data, you wanted to choose 70% of them will be trained first. And it's completely random. For example, the 70% of your data will be coming from here. So 509 times all your factors. For example, these are your 30%. And the remaining would be your training split. So these training split will be compared to your ID and IV. So again, your training split will be compared your ID and IV at first. So let's say in your training, you'll receive 80% accuracy model. What about for your testing split? So your testing split will be the remaining percentage. If you already trained 70% of your data, then that means you're left with 30% testing. Why does testing come after your training period? Because in the testing phase, it's like you already wanted to find your final accuracy model. So the importance of training, it's like a testing and error. You wanted to train your model first before you can even find the actual accuracy of your overall model. So for your 30% training, testing, sorry, it will reflect the remaining data, this one. Okay, so just an example. For example, this is your 30%. And then most likely in A and N, testing is almost always higher than the training model. Let's say 92% of accuracy. Why is it always higher? Because you already have your standard data. You already trained your model. If you've already trained your model, then that means your model can definitely find what's the perfect solution, what's the perfect optimizer, or what's the perfect code, what's the perfect hidden layer, what are the perfect factors that you need to maximize in order for you to increase your accuracy model. So it's like you wanted to eliminate all your inhibitions in the training part. You wanted to eliminate all the incorrect optimizers, all the incorrect hidden layers, and replace it with a more accurate one. That's why you will always have higher accuracy compared to the training accuracy. Okay. And then for the next part, we have to, I'll copy this one. For this part, you have to import your Excel file. So you can also utilize your CSV. So let's go back to our CSV file from earlier. This is the one that we have. I'll go back to the CSV that we have computed when we incorporated supervised learning into the PSO k-means algorithm. So as you already know, we have computed the ID and IV. What about for others? We just have to input their average values. So just compute their average. I'll just put it as EE, average value. Oh, I think I removed the EE1 here, so you can just input your EE1. So average value, and then your U. You should also find the average value. For PV, average value. And then average value for PS. And then for PEC, for SN, for A, you can actually code this part in the spider, but it might be too tricky, so it's better to manually input the CSV file first. But for the rest, you can opt to find their average value using the spider method. But I would not suggest utilizing the coding part for this one, because if your data is already incorrect from the get-go, then most likely the rest of the model will also be incorrect. And then OT, average value of OT. Then finally, FC. Okay. I think I deleted EE1. I'll just find it again. Okay, this one. Okay, so now that you already have your average value, oh, where are they? This one. Now that you have your average value, you can create your new sheet. So let's copy all your average values. EE, UPV, and then PS, PEC, your SN, AM, RIOT. Then finally, the last variables. Okay, so you have a total of 11 latent variables or 11 independent variables, and then two target class or target variables or dependent variables. So you should put this one in these leftmost parts so that this will be the part that's going to be read by the model. So let's save it. And everything should be unique, should be EEUPV. So all your variables should be unique. And then let's copy this Excel file, CSV file rather, and then you should paste this one. That's CSV. So it's almost similar to the MATLAB in this part. It's just that we have to code it in a different way. When we say this one, read CSV, it's almost similar to this one. But if you notice, we call it out as dataset. In the Python, we call it out as DF. DF means data frame. So it's just similar. It's just that your dataset and DF are in similar contexts, but have different codes, implications depending on the coding tool. Why do we need to have this head? When we say head, we're talking about the headings, these one. EE1, EE2, EE3, EE4, these are the headings. So let's run this model. You can notice it from this part. Okay, this one. You can print it. Print meaning you wanted to know. Oh, it's error. Oh, it's error. If you receive this kind of error, meaning they're not in the same folder. So this one should be, where is my untitled? Where did I save this? I'll just save it again. Oh, in a different file. I'll save it in this folder. So they should always be in the same folder. So let's run it. This one is run. Okay, so no error already. And you can notice that these are our headings, data frame. You can verify your code in this part. So the first one talks about the row. The number of row is the number of your participants. And the second number pertains to your number of column or the number of all your latent variables. So you have 11 independent variables and 2 dependent variables. That's why we have 13. And you can also check over here that it correlated to everything from EE up until IV. So why do we need to print this part? We have to print this part. It's like this one. And then describe. Describe, it's like a statistical descriptive analysis. Okay, so if you wanted to know what are your mean, standard deviation, minimum, and any other kinds of descriptive analysis, you can utilize this code. But if you don't want it, you can just have these number sign. And then the next step for us is to, I'll input this one. Sorry, this one first. What do we mean by group by? We wanted to just really group our 2 variables. We wanted to group one independent variable into another dependent variable. So I'll choose EE first. Let's say EE. And what was the other one? ID. Again, this is your independent and dependent variable. And then this is your this is your dependent variable. And then this is going to be your independent variable. Okay, so again, we have to choose one among all the independent variables and another one for the dependent variables. Why? Because we wanted to find how important EE is to ID. When we say label, we wanted to find the dependent variables. That's why we called out ID or intention to the need. When we say features, features are what we also call as independent variables. So in the usual context, we call them as independent variable, but for ANN or any kinds of machine learning algorithms, we should always call them as features. So how can you know if you were able to call out the right variables? By simply printing the labels. When we say labels, again, we're talking about dependent variables. From 0 to 5, it talks about from your 0 row up until fifth row. So let's run it. Okay, so you'll notice that this pertains to 4, 3, 1, 5, 5. If you're going to look back into your Excel file, this one, your ID should always be equal to 4, 3, 1, 5, 5. So these are your first 5 rows. These are similar to this one. Okay, this is one way to check if you're calling out the right variable. What about your features? We also wanted to check if your EE is properly called out. So let's print it. So it's this one. From U to IV. You can also, oh, it should be this one. From U to IV. But the thing is, if you notice, why did we remove EE from this part? We removed EE because of this code, the drop. Because in ANN, we already wanted to know how important EE is once we remove them from the model. So in the model, let's go back into our ANN. If you're going to check how important your EE is in the model, you don't need to include them in the input layer. You also don't need to include them in the output layer, of course, but you don't really know if it's included in the hidden layer. So we'll never really know if it's included in the hidden layer, but one thing's for sure is that your EE is not included in the input layer. So it's kind of in a vice versa technique. You in A and N, you wanted to check how important the variable is once you eliminate it from the model. It's not the other way around wherein you have to eliminate from U to FC in order to identify if your EE is one of the most significant model. So it's on the other way around. If it's not included in the model, but you produce the highest accuracy rate, then most likely in any way around, most likely it was included in the hidden layer, but we don't really know how many hidden layers, how many kinds of EE hidden layers did the model was able to incorporate into the overall model. Okay. Next part is this one. For this code, For this code, we just wanted to assure that our 1 is equivalent to 1. Our 2 is equivalent to 2. 3 is 3, 4 is 4, 5 is 5 for all the labels. Again, the labels pertain to our dependent variables. Why do we have to call them out one by one? Because sometimes in MATLAB, your variables turn to, or your numerical values rather, sometimes although you called it out like this, sorry, this, for example, although you called it out as 4, sometimes while undergoing a lot of coding, a lot of formulas involved in your arrays, it might have 4.1, or let's see, it might be called out as 4.01. So that means this is not already considered as a class, because in class, we always have to keep everything in a non-decimal numerical value. So that's the importance of calling them out in this code. Next is to find our features. So this is just very similar to the ones we used earlier. So you just have to assure that your features are called out except for EE. Okay, so this one. And then for the next part, this code. For this code, your float 32, it's actually a package for you to identify what's the right feature and what's the right label. So it's like you wanted to, for example, you wanted to change the array of your model. Let's say right now, they are currently in this array in separate table, let's say in separate table based on the Excel file or the CSV file, but we wanted them to combine. That's the importance of float 32 package. So for example, let's print our features. It will be like this. So if you remember the one with brackets earlier, it's actually easier for the code to do all the codes, to do all the operations once they are in array like this, in bracket. So you have to apply everything into array for features and labels. So like this one. Okay, so everything is taken into consideration. And if you notice, we have 12 in the last part. This actually pertains to these print len features. So I'll run it again. You have to ensure that your variables is equivalent to -1. For example, you have 13, this one, you have size of 13. Then -1, it should be 12. Why? Because you have eliminated EE. So you always have to minus everything into 1. So that assures us that we have already eliminated EE from the input layer. And then next is to split our model. So a while ago, we talked about this code, this one, the train test split, because we wanted to ensure that in our model, we wanted to ensure that the data is splitted according to its proper training and testing size. So in this part, you have to change this one. You can change it into this means 30% testing set. You can also change it to 20% testing set, 10% testing set. If it's 10%, it should also be 10% in this part. This is to ensure that our labels and our features are aligned, or always aligned with each other. And the ideal testing size would be just about 50% up until testing size, 50% up until 40%, because automatically your training size will be the remaining figure. So if you have 50% testing size, you'll have 50% training size. If you have 40% testing size, then automatically you'll have 60% training size. Oh, I was signed out. Oh, am I still here, Doc Yogi?
Yes, you're still here.
Okay.
Can we just run one?
Okay. I'll run one. But why was I signed out in the Zoom? I don't know.
No, you're fine. Let's run one.
Okay.
So let's just run one and then we can continue this one again next week.
Okay, sure, sure. Okay, so I'll stop for this one and then explain the rest of the codes the next meeting. So I'll run this code. Oh, this one is from one of the, I think yes, it was already published. I utilized a lot of feature engineering principles before I utilized the AN part, so you can also utilize that one. Or let's say you can also utilize SEM before inputting them into the ENN part. But I would not really recommend SEM because SEM is already can already stand on its own. So I do not recommend SEM, but you can recommend I can recommend a lot of statistical formulas like the correlation, univariate, the ones that are not really stable enough. ANOVA can also be a possible. Okay, so this is your model. This is your training accuracy. That's about 9.07%. And this is your testing accuracy, 100%. But we have 150 epochs. 150 epochs meaning 150 runs. So it's like our iteration from the PSO. In PSOK means we have the iteration part, but this in ANN we do have the epochs. This is your plot. You can click this one. Mm, You can save the plot like this.
We can zoom it. Yeah.
Mhm. Okay, this one. So it's not a good model already. So you
Yes.
can notice in the ANN, what's a good model? This one is a good model. If the green part is actually your validation, it should be, yes, it should be the testing, the green part, and then the blue part. A good model is something that has close proximity to these two, but also has a curve like this. It should always be curved like this and not curved like this. And as you can see, our green line is actually above the blue line. So it definitely shows that this is a poor model. Oh,
Can
am
you
I
show like
correct?
one good? Can you show one good model?
Okay. I'll try a different one.
No, just show like one
Oh,
your publication perhaps. That's your preferred. Yeah.
okay.
Yeah. And we can just stop up there here. I know two of them already got the headache. This is not the thing that you
Okay.
can learn within like 1 week or 2 weeks, guys. This is so many hidden things, under that.
Mhm. Mhm. Because they asked me to remove this part. I don't know why. They mentioned it's unnecessary.
Well, I think for some people they do not really need that
Mm-hmm. Yes, yes.
because just using like one line, you already can see that, you know.
Mm-hmm. Yes. Okay, this
Yeah,
part.
that one. Yeah.
Oh, sorry. Oh, sorry. I think I was incorrect earlier. The training part should be the blue one. So
Training is the blue one.
yes,
Yes.
I thought it was the green one. So the training should always be lower than the testing part. So if you notice, this is a good model. Why? Because it's not only having a higher training accuracy model, but also having that curve. If you notice, it started from having lower training accuracy in this part up until it had a higher training accuracy. So you'll definitely notice the big, let's say, significance between the training and then the testing accuracy model. There is definitely a better model than this one, but um the good model is something that really required having this one. No spikes like this, no spikes like this. So that's a good model. But if you can only show one figure like this, it's already fine. And I think some reviewers don't really like this kind of model because they asked me to remove this part.
Can you just draw like zigzag things, you know, so like there, like
Mm.
can you give one example, a bed model? Yeah,
Oh, okay. Oh, a
zigzag like
bad model. Oh,
yes,
for example, this one.
overfitting model. Mhm.
Mm. Oh, overfitting. Oh, overfitting. If they are like this, overfitting, your green and blue are almost just the same.
Mm.
This is already overfitting. If they don't have any proximity like this one, they should have at least a small gap, but not too wide. You can definitely notice it from the values itself. If you have 97%, 98%, so that means you have a good proximity value. So this is overfitting, and this is an example of underfitting. This is your training, and then this is your testing. This is underfitting, not only because they have wide proximity, but also because your training accuracy, this one is testing. It has lower value compared to your training. So it should always be testing greater than training. Okay, so I think that's it for me for now, Doc Yuki.
Okay, so let me stop the recording.